Good morning and welcome to the Northern Institute Visiting Scholar Seminar Series for 2025. My name is Sigurd Derting. I'm a researcher at the group of Demography and Growth Planning. And first I'd like to begin by acknowledging the traditional custodians of the lands on which we meet. Those of you joining me here in Darwin, they are the Larrakia people. And I pay my respects to the Larrakia elders, past, present, and progressing. And I extend that respect to all Aboriginal and Torres Strait Islander peoples joining us today. Today it's my great pleasure to introduce to you Kazu Hanaoka. Kazu Hanaoka is an associate professor in the Department of Geography at Ritsumeikan University in Japan. His research spans a number of areas, including spatial microdata simulation, temporal and spatial analysis using mobile phone data, which you'll hear about today, as well as the analysis of census data, looking into the mobility of foreign-born residents. He is also the former director of the Institute for Disaster Mitigation for Urban Cultural Heritage at Ritsumeikan University. And the topic today that he will talk about is mobile phone big data analysis and the COVID-19 pandemic. Kazu, over to you.
Thank you very much, Sigurd. And good morning, everyone, and thanks for coming. And today I'd like to thank Northern Institute for giving me opportunities for my presentation. And as Sigurd mentioned, today I'm going to talk about mobile phone big data and the COVID-19 pandemic, as well as some progress reports. I presented a part of this topic at a seminar 2 years ago, but today I'd like to include some recent developments, what I have done. So, just a moment. So first, introduction. Okay. So we are seeing a new forms of big data and analytical method coming like a big wave. So I'm a member of Department of Geography, and traditional disciplines such as geography and also the geographical information science are now moving toward big data science. Today, massive data sets are being generated from social network services, transit cards, and smartphones. Feel very quiet. Is that okay? Can you hear my voice? Okay. Clear? And those such fancy data are analyzed with artificial intelligence. But looking back to the around early 2010s, in Japan, big data in particular, mobile phone data began to appear in the market. Some companies start to provide their data set to university researchers. And this marked a major turning point because before that, mobility research, such as studies on commuting or the consumer behavior, relied mainly on questionnaire surveys, which are infrequent and also covered only small samples. So nowadays, a variety of the data sources available to understand human mobilities. But each data set has its own advantage and limitations. Mobile phone location data can be categorized into two types based on the data collection method. The first type is cellular tower-based data, which uses a cellular tower connection to find the location of mobile phones. And since all mobile phones are constantly connected to the nearby towers, the location can be continuously recorded. The advantage of data is its large coverage, but they are usually aggregated by the grid cell like 125 meters or 250 meters. The second type is mobile apps-based data, which uses GPS and Wi-Fi networks for positioning. Usually, users agree to share their location data when they install apps. So XY coordinates are recorded every 5 or 10 minutes while they are using apps. So therefore, we can trace users' trajectories with very high accuracy. However, there are several limitations. For example, trajectories sometimes contain a lot of noises due to the inaccuracy of GPS positioning. Also, users may stop using apps, so the data are not collected over a long time period. So this map provided by a good corporation, and it shows the movement of trajectory of people who entered or left Kyoto City. So here is the Kyoto cities. So most of these movements represent commuting or school trips around the Kyoto metropolitan area. However, you can see the inflow from Tokyo shown on the right on the map. And you see that some artificial straight lines maybe represent a long distance trip by bullet train or airplanes. So this kind of massive size of trajectories can be visualized very easily using Kepler.gl, which was developed by Uber. And the data set I show you here is very similar to the trajectory data I use for the further analysis. So around 2010, when the big data first appeared in Japan, mobile carriers began to providing cellular-based mobile phone data aggregated by grid cells. Our case study with David and is one of the early examples that apply this kind of data for disaster research. So when an unexpected event occurred, like natural disasters or pandemics, mobile phone data are especially useful for tracking population movement in near real time. For example, even 5 years after the Great East Japan earthquake in 2011, a population recovery in Fukushima, this is the Fukushima area, remained limited due to the nuclear power plant accident. The population distribution in Fukushima after the accident was observed using big data derived from mobile phones. So this map on the right shows a spatial distribution of population within the evacuation zone. So this is the evacuation zone. So you can see that all coastal communities shown in the dark brown or orange on the left side maps for small communities are all gone after the accident. And only a small number of the workers from electric power companies and the decontamination company stay there at that time. A second example is mobile phone can be used to study crime analysis. So maybe some of you may have heard of the routine activity series, but it suggested that absence of guardians is one of the 3 key factors that can lead to the crime. So we can measure natural surveillance by citizens by using our ambient population, like this one, which comes from the mobile phone big data. And our study found a quadratic relationship between ambient population and nighttime crime occurrences, so like this one. And it means that during the nighttime, offenders can more easily find a suitable target. Offender can more easily find a suitable target and occur crime because there are fewer guardians in the dark. But this is not the case during the daytime. The third one is the big data from mobile phones are also useful in the fight against infectious disease. During the COVID-19 pandemic, the going out rate in the city center estimated from the location data of mobile phone users was frequently reported on television and in newspaper in Japan. I'm not sure in Australia. No? So the government, also the government ministry in Japan have also used the big data provide different type of information, including people's movement and also the consumption pattern to understand the effect of the pandemics. So as a result of these experiences, I think the public attitude toward mobile phone big data or the big data in general have become more positive in Japanese societies, but to some extent. So in relating to today's topic, already a number of the studies have been published. So that they analyzed the change in the people's mobility during the pandemic. For example, in Tokyo, in Japanese government asked non-compulsory measures against COVID-19 pandemic, COVID-19, but it is sufficient to reduce the people's inflow to the city centers, and also reduce the number of the cases. Also in Osaka, in other parts of the cities, compared to with the pre-pandemic period, spatial extent of the people's activity space was reduced by half during the pandemics. So we found that these findings are already reported, and then the more coming after, I think, 2001. Also, other studies have reviewed the social network and the community structure using mobile phone data. Location and course flows mobile phone users were employed to reconstruct interaction and functional area among the residents in order to examine the social and spatial segregation. However, the missing point is that long-term behavior changes during the pandemic period, as well as variation in the movement of the people, have not been fully explored throughout the one city. So this study, the aim of this study is to understand spatial temporal distribution of people in Kyoto City using mobile phone location data. In particular, our analysis focused on long-term changes, so the 2 years changes, and also the regional differences within the city. So our study focused on Kyoto City, Japan, which has a population of about 1.5 million people. And as an ancient capital cities, Kyoto City attracts many domestic and international tourists. And this study covers a 24-month period, so 2 years from January 2019 to December 2020. So we use a mobile phone location data, practice smartphone apps provided by the company named BlogWatcher. The data set covered the 2 years and include a trajectory of both residents and visitors. And all trajectory data of people who entered or left Kyoto City at least once during the given month are available. So the total number of recorded points for the 2-year period in total is 48.7 billion data points of XY coordinate, which is 4.42 million unique smartphone IDs. And also the XY coordinate recorded every 5 or 6 minutes on average. So the huge data set, and I think this is the biggest data set available, mobile phone data set available in Japan. However, before the data were provided, various privacy protection procedure had already been applied. For example, a home location and also workplace location were represented by the centroid of 125 meters grid cell. So I don't know the exact location of home and workplace. So in addition, showing this slide, several procedures were implemented to the trajectory data themselves. So the data points were reviewed, and if necessary, some points were removed, or some random noises were added to protect privacy. Because the data set was too large to process, we extracted only stay points from the trajectories. So a point was defined as staying when the speed was under 30 meters per minute, and the distance of the 2 points was less than 40 meters. And for the calculation, outliers from the weak GPS signals were removed. So this is a very simple way of the simple method to calculate stay point, but there are different type of methods available, like using more sophisticated clustering techniques and so on. But this is very simplistic, the most simple way to calculate. So in addition, if 2 points are very close, 2 stay points are close enough, I try to merge them into the 1 point so that I can reduce the stay points, data points further. So finally, we extracted 110 million points for the Kyoto City. So where people stayed for more than 10 minutes, this is so the 110 million points is the points where people stayed more than 10 minutes. So this map, this map shows our Ritsumeikan University campuses, and you see that the 10 dots are equivalent to the stay points, equivalent to the stay point. So you see that they are located on the buildings, usually staff and students stayed. So generally, our simple method provides reasonable results. But in the following analysis, the time spent on weekdays and weekends was calculated using different spatial units, such as 250-meter Spatial or distance band from the homes. So here are some other examples taken from historical district and the museum district. So this is a very famous tourist site. And this is, there are 2 museums here, and you see the little dot concentrated on the building of the museum. So using these data sets, we try to analyze these 4 questions. The first question is, to what extent have Kyoto residents changed their activity space during the pandemic? Second question, where did Kyoto residents go on weekends within the city? Third question, where did residents of the particular neighborhood stay in the city? So last question is, where are people from different regions likely to encounter each other? So first question is, to what extent Kyoto residents have changed their activity space? So this graph shows a percentage of time spent by distance band from users' home over a 24-month period from the 1st January 2019 to December 2020. The percentage of people staying within 240 meters of their home, showing the green bar. This is kind of the stay-home ratio. And this ratio remained just below the 80% before the pandemics. But after the pandemics, the ratio goes up to, or it has exceeded 80%. And even after lockdown ended in late May 2020, the value remained around 5 points higher than before. So you see the level is higher than before slightly. So people continue to stay home even after the lockdown was ended. So this is the second question. Where did Kyoto residents go on weekends in the city? So I calculated the total time spent by Kyoto residents outside their homes on weekends, and I aggregated those time by 250 meters grid cells. So you see that the map on the left shows the situation before the pandemic, and the right is during the pandemic. So you can see the red area. This is the city center, and this is a central station of Kyoto. So people used to go out to the city center or near the big railway station for shopping and so on weekend before the pandemic. And the comparison of these two maps clearly show that during the pandemic, residents avoid visiting the city center and spent more time near their homes than before, because we can observe fewer red cells in the city center and near the major station, and more yellowish green cells in the suburban area, which means that more people stay there. So the people enjoy visiting park near homes and so on. So I think it's very similar to Australian situation during the pandemic. But when we look at the third question is where did the resident of the particular neighborhood stay in the city? So we try to look at the focus on the one neighborhood and to look at their spatial behavior. So that we selected the 3 suburban neighborhoods. So 1, 2, 3 suburban neighborhoods, and calculate kernel density of their stay points for 3 months period in 2019, so before COVID and during the COVID. So residents in these 3 areas tend to stay close to home. In both, you see, I'm not sure you can see clearly, but generally their activity space is close to their home, but you see a lot of, they visited the shopping malls or supermarket, hospital, and or other places across the cities. And when we compare the before and during the pandemic, the spatial the extent is very similar. So people still continue to travel. People continue to travel widely across the city, but they try to avoid the city centers because a lot of stores are closed, and also they are worried about social distancing in the densely populated city centers. So we can find that their spatial behavior during pandemic, their spatial range, they are very large, but they try to avoid the city center. So this is a fourth question, is where are people from different regions likely to encounter each other? So I produced the maps for each month from January 2019 and 2020. And I calculated the diversity index of origin of people based on information entropies. So the index takes its lowest value when all visitors come from one origin, and the higher values when visitors come from different, so various origins. So in the 2019 maps, for these 5 maps, you see, the area with high diversity index can be observed in the city center, and these areas can be too small to see. So these these small concentration. Here is famous temples or shrines are located, so the tourist site. And these, yes, so this is before the pandemic, and during pandemic, particularly after the lockdown, these diversity index dropped significantly, particularly in May 2020. But it gradually recovered after the lockdown was ended. So you see that people are more, again, flow into the city centers for touristic site. So when we look at changes in diversity index by regional type, we classify the area into high and low diversity groups of April 2019, so the before the pandemic. So in the area, in the regions with high diversity, the index declined significantly during the lockdown, but rose again soon after it's lifted. In contrast, in the lower diversity regions, mainly to the suburban areas of the Kyoto City area, continue to decline even the state of emergency has lifted. So in the residential area, people continue to avoid meeting visitors such as relatives and friends from outside Kyoto cities. So there are two contrasted phenomena observed from the diversity index. So I try to summarize what I found from the mobile phone big data analysis of the pandemics. So the first one is during the pandemics, the percentage of people who stayed at home increased by more than 10 percentage point in May 2020 compared with pre-COVID period. Even after the state of emergency was lifted, it did not return to previous levels and remained about 5 points higher. And the people moved widely across the city, but they tend to avoid the city center, where the social distancing was difficult to maintain. And many stores were closed following the government request. These changes in the people's attitude and the spatial behavior were revealed and visualized using big data from mobile phones. And third point is based on our long-term observation of people's movement, visitors from other regions almost disappeared during the outbreak. After the state of the emergency ended, the number of visitors from the various prefectures recovered rapidly in the city, in the city center and touristic site, but not in the residential areas. So in conclusion, mobile phone big data allows to analyze long-term changes in people's movement at very fine spatial scale and temporal scale. And in next step, we plan to add more data set to analyze the people's changes after the pandemic. And from this point, I would like to share some more experimental data visualization as part of our progress report. So first one is in Kyoto cities, we have a large festival every July. So during the period, floats like these pictures are showing in the street or displayed in the street. So using mobile phone data, we can identify, so these are location of the float. So we try to identify where the crowds are formed in the cities. However, one limitation of this data set, so the stay point data set, is that it cannot distinguish between indoor and outdoor location. So to address these issues, maybe we need to further use the information of people's movements before and after each stay point, so the context. So stay point can be also be utilized in the retail sector, for instance, to estimate the customer volumes for both one's own stores and also the competitors. For example, we estimate the hourly volume of visitors staying in the shopping malls. This graph shows that the changes between weekdays and weekends before and during the pandemics. So on the normal day, the two peaks can be observed around the noon and also in the evening. However, during the pandemic, the difference between weekend and weekdays become very small, and the pattern changes to flatter distribution with single peak around the midday. So we arrange the hourly volume graph over the entire month. They resemble an electrocardiogram of the city. In a healthy state, we can see the steady rhythm of daily activities, like a regular heartbeat. However, during the pandemics, the bottom is the pandemic, so 2020, and this rhythm became irregular, and almost like arrhythmia or even a flat line. So this is an example of the touristic area. More significant changes can be observed before and during the pandemic. So the heartbeat almost faded during the pandemic, as shown in the graph at the bottom. So because we know where people from where to where, I mean, we know that the trips, we know that a lot of trips within the cities. So we try to apply the cluster analysis to the origin and destination matrix of the people's movement. This analysis successfully identified the nodal regions, visualizing the resident interaction zones. So traditionally, these regional classification can be done based on census data, and so the commuting data or the census data or person trip surveys. But using a big mobile phone big data, we can create this type of nodal region maps with very high accuracy. Also, we can make the nodal region maps for particular time, for example, nighttime or daytime or spring or winters. We can create this type of maps. And in recent years, we have been collaborating with researchers at University College of London. And we have developed a dashboard application to explore the population distribution or time of the day, so that the data can be visualized like this way. Also, we try to study the route choice of the people. So people do not, maybe we do not always choose the shortest path. Maybe we sometimes choose a detour to visit shops or and so on. So people tend to choose a more comfortable environment. And particularly in Kyoto area, we focus on the greener surroundings, and which is measured by the NVBI, vegetation index. So the project aims to understand the route choice behavior and its determinant using our mobile phone big data. And our analysis showed the two key findings. First, people tend to choose the shortest path around their homes. So they know the shortest path around their homes, but not in the area where they are familiar. So their routes are finding more heuristic. And the second finding is environmental qualities have significant explanatory powers. So the greener streets, like which has street trees and so on, people tend to choose those comfortable environment when they select the path. So these trends are particularly obvious during the summertime. In Japanese summer, it's very hot, like Darwin. So these findings can be incorporated to diversify pedestrian route choices, route choice modeling, and also create synthetic reconstruction of movement. So these findings can be incorporated in the analysis. So that's all for my presentation, and it's a little bit general, but maybe you understand how the big data can be used, and we welcome any questions. Thank you very much.
Thank you very much, Kazu, for the fascinating talk. I'm sure there's going to be lots of questions.